Hello everybody. Today we will talk about circular motion and we will concentrate on uniformly accelerated circular motion as I will explain in the slides. So first of all, what is a circular motion and what is characterizing circular motion? The thing that characterizes circular motion is what's called angular velocity, and I will tell you what it is. But first, have in mind that the circular motion is, think about an object that has a mass that is moving, but the trajectory of the object is a circle. Is basically the body trajectory lies on a circumference. So at each point that you take a picture of it, for example, a snapshot of the motion, you can trace back the position and it will be at a distance r from the center for all the position in time, and it will be a periodic motion then. Okay, so you can think about we can think about specific case. For example, if you think about Earth rotating around the Sun, even though they are ellipses, you can approximate them well with a circle. The difference from circular motion and elliptical motion is that there is a bit of change in the velocity along the radial direction. But we will talk about that briefly. But the idea is that a motion, when a car is racing around a track, a circular track, or when you are rotating an object attached to a string, rotating around your head before flinging it, for example, that is considered circular motion. So you have to think about that at each moment of time, the velocity changes direction. Okay, so this is a crucial point in circular motion. At each point of time, there is an acceleration towards the center, which is called centripetal acceleration, and that acceleration changes the motion at each time, change the direction of the motion. Okay, we will say that in a uniform motion, this acceleration is constant, and also there won't be another acceleration along the direction of the motion. So, as I said, so there are few things that we need to keep in mind. Is that the velocity at which the body is moving is tangential to the trajectory. Okay, and this is because basically the rate of change is towards the center. So for a bit of space in the tangential direction, you then drop a little bit in the radial direction, and this makes it a tangential velocity, which basically tells us that gives us basically the rate at which the object is orbiting around the center. And then, of course, we already said that there is an acceleration toward the center that is usually caused by an external force. It could be the tension of the rope that you are rotating, or it could be the pull of gravity from the sun. But basically, this force creates an acceleration towards the center, centripetal, which will change the direction of velocity at each time. And then in general, the acceleration may have component along the tangential direction as well, or along the direction of the radius. So if you are in a circumference, because you are going in uniform circular motion, you can be changing your trajectory by enlarging or reducing the radius of the motion by changing the velocity or changing the definitely change the acceleration. So if you drop the velocity, you will, or if you increase, you will change the orbit, and if you boost the acceleration in the radial direction, you will change the radial velocity as well. So yeah, before going any further, let's do some example, and then let's define, let's put some names on what we define. So this is the radius of the center, this is the circumference, and think about the motion that goes from left to right. and then we have this angle alpha and this bit of trajectory here. Okay, so of course alpha uh, changed in time, because alpha was 0 at the beginning and then it was maybe 30 degree after a certain time. So there is definitely a change of time over alpha, and actually I will call it phi for a reason that it will be clear later. Phi, this is called angular velocity. Angular velocity, okay? It's the rate at which the radius is moving, okay? Of course, the angular velocity will be the same for all of these points here, because they are all lying on the radius. But what is changing differently is the tangential velocity. So the velocity orthogonal to the radius. That one is different for each radius, depends on the radius. The point actually depends on r, small r. Because of course, if you are very close to the center, in the same time that the radius going from point 1 to point 2, you will have traveled a different length. Okay, so the tangential velocity is different from r, and there is a nice relation between the two, which is omega r is v tangential. Okay, we will see that in a sec. Okay, so angular velocity is the rate at which the radius is sweeping the circumference, and this is fixed. It doesn't change in time. Yeah, so the omega in dt is 0 for uniform motions. And also the tangential velocity, at least the magnitude of it, is 0. But of course, we can see here that the direction changed, because here was pointing in this direction and here is pointing in this direction. So there is an acceleration that is playing a role there, which is the acceleration towards the center along the radius. Okay, so this is just a sketch of what we need to understand about the circular motion. Okay, and of course it's periodic, because the motion after a certain time t, which will go back to the same position here. Okay, exactly like the Earth around the Sun. So as you said, there are these two distinctions to make: angular and tangential velocity. They are related to another, as we just saw, by the formula. This formula omega is r times v tangential divided by r square. This is the cross product between the radius and the velocity at the tangential point, and r square is the distance square, and this is the angular velocity. These in turns relate the radial and the angular velocity to the tangential velocity in this way, in a circular motion, because basically the cross product, as you remember, is r times v sinus the theta, and theta in this case is 90 degrees, because they are orthogonal since it's a tangential velocity. So I mean, we have this formula here for the vector product here, r times v tangential, exactly. So the sinus is 1. Okay, so okay, so we have cleared the difference between tangential and radial. The radial velocity is the component along the radius, and the tangential velocity is the component tangential to the trajectory. In a uniform circular motion, there won't be any radial velocity, because the radius is fixed, so there is no change in motion. for some reason you have to, if you for some reason change the tangential velocity, you will change the radius as well, of course. Or if you change the angular velocity for some reason, you will change the tangential velocity, keeping the same radius. So there are these two things that you can keep in mind. Okay. So of course we said that the angular velocity is the rate at which the radius is sweeping the circle. So you can imagine that at each point in the radius you have the same angular velocity, because the angle after all is changing by the same amount. You're changing about the angle phi. So phi is whatever is here. It doesn't matter where you are in the radius, the angle is the same. The angle between this point and this point, this point and this point, and this point and this point are the same, but the trajectory is different. So you have to bear in mind the angular velocity carries information about the rate at which you can, and actually the angular velocity is 2 pi over the period. It's the periodicity. It's important because it carries information about the period of your t is the period of your motion, but it doesn't carry information about the energy, because there is no, so of course a particle moving in the center is way slower than a particle moving at the edges of the circumference, because the tangential velocity will be different. So angular velocity is important to understand the periodicity, the period, the frequency, but the tangential velocity will give you more information about the energy. Okay, so these two things have to be clear in mind. Tangential and angular velocity will carry different information, although they are related one to each other. So as I said, so we can do another drawing. So this is a part of a circumference, a larger one, and then there is the radius of curvature that is fixed, and this is also the radius, the distance is fixed. And the tangential velocity is the one that goes in this direction, and this is 90 degree. And then the radial velocity is the one that is going in this direction here, velocity radial. Okay, if there is a change in the radial velocity, there is an acceleration along the radius, the object will fall in a different trajectory, because it will move from here to there. And if there is an acceleration along the tangential velocity, the rate at which, different from zero, the rate at which the speed, so the period, will increase. So t0 will become minor than t1 if the tangential velocity is different. But in our case, we said that we have no velocity along the, well, no change in velocity along the radius, so the acceleration around the radius is the same, and there is no change in velocity along the direction, the tangential direction. So this is a uniform motion. Meaning that omega is constant. This is very important. The angular velocity is constant, meaning that phi d phi over dt is omega is constant. So there is no acceleration in any of the direction. Okay, so this is just a picture, a bit more clear picture of what I mean by tangential. Tangential is when it's 90 degree with respect to the radius, and orthogonal, which is also orthogonal, sorry, it's also orthogonal. And the radial acceleration is the one along the radius. Okay, so I hope this is clear. And then we have some usual formula that we have written already. We can say that omega is the rate at which the angle is changing over time. That is also omega is also the radius cross product of the tangential velocity over r square. But there is another one that is important. There is the acceleration. That is the derivative over time of r t divided r square. And this is a bit of a beast because there will be two components. There will be two components. One that it will be related to the radial acceleration, and the other there will be plus minus actually a component that will be derived by the radial plus r times v, 1 over r cube. But and this is because this is a product, so we'll have two components, and this is a derivative, so you have also the derivative of the fraction. But this point here is important to note that the change of r in time is 0 because it's a uniform motion, so we can safely forget about this part here, which is 0. And then we can say that in uniform motion the acceleration is only given by the radius cross product, the acceleration times r square. Okay, so these are important formula. And then the other one that we need to remember is that the angular acceleration is 2 pi over the period. Okay, and the period is the time that it takes to reach the same position at the beginning. Okay, so RT is 0 because remember that is a uniform circular motion. Okay. The circular acceleration is whatever we already introduced it, is whatever it's changing the velocity in either the tangential or the radial direction. In the uniform circular motion, the one that we are dealing with, the derivative of v over t, so the tangential acceleration is 0, at least the modulus, but the direction is not 0, so at is well, at is 0, but a radial is different from 0 because, but it's different from 0, but the derivative is 0, so it's uniform, it's constant, so you have the same fixed acceleration, which is called centripetal acceleration. Okay, and it's directed towards the center of the object, which makes it keep in the trajectory. Without this acceleration, which is caused by a force, usually an external force, it could be the tension of the rope, it could be the pull of gravity of the earth, this acceleration that keep changing the velocity at each time will make the motion circular, and if it's constant, it's a uniform circular motion, as we said. And I think with this we have finished the lesson. So we will summarize the useful formula that we derived. So the change of the angle is called angular velocity, but the angular velocity is also given by the cross product of the tangential velocity over r square, which is also written as this, and this is because the velocity and the radius are at 90 degrees apart from each other, 90 degrees. So the cross product simplifies, and then we have the acceleration over time. We said that in the uniform case is the acceleration in the tangential divided by r squared. And this is when the derivative over r over time is 0. So and this is in the uniform case. And then we need to remember that omega is also related to 2 pi over t, where t is the period, which is the time that it takes to the particle to get to the same position as it started from. So for example, the Earth around the Sun is 365 days roughly, or whatever rate at which you're spinning your object. Okay, I hope that this was clear. Follow for more will exercise will follow on this, and see you next time. Thank you. Bye.